Hello. Hi. So today we're gonna continue on what we started yesterday, which is essentially understanding the connection between matrices and vectors and vector spaces and geometry and all the stuff that we've seen in the introductory part. Okay, so let me go through some fundamental definitions that we've already seen. Okay. And do some reminders. Okay, so what do we know so far? Well, we know many things, okay, but we start to understand that there's something called a structure called vector space and subspace. Okay. So very quickly, what do we know about these things? What do you know, for example, about vector space? So, examples. Let's start with the easy things. What are the examples of vector spaces that we have seen so far? Well, the usual geometric Euclidean vector spaces. Okay, so examples. RD, okay, or D and A. That's also known as the Cartesian Euclidean space. Okay, so this is Cartesian Euclidean space. We call it Cartesian Euclidean because Euclidean doesn't necessarily have a reference frame. Okay, so this is essentially what Descartes did. He put a reference frame to Euclidean geometry, right? And once you do that, you realize in modern mathematics that this is just the Cartesian product, R plus R plus R, yeah? As many times as you want. Of course, geometrically, this means this has a geometric meaning in R1, R2, R3. Beyond that, we still call it geometry in maths, okay? But of course, it's not like usual geometry. It's like more kind of high-dimensional geometry, okay? Which is geometry in its own right, okay? Good. So this is one example. But we've seen other examples, okay? Very quickly, we didn't have time to go very deep in that, okay? But we saw, for example, that the space of polynomials of some degree, say, k, okay, for some k in n naught, is actually also a vector space, right? And we saw also that, so these are finite dimensional vector spaces. Okay, the dimension of RD is D. Okay, so roughly speaking, the dimension of a vector space is the number of free parameters that you have in them. Okay, so how many free parameters you have to describe a vector in RD? D of them. Okay, so we call it dimension. Okay, that's the intuitive idea behind dimension. Okay, the mathematical dimension. How many free parameters do we have to represent polynomials of degree k? How many do we have? K. Well, let's remind ourselves. It's almost there. Okay, let's remind ourselves what is a polynomial. Okay, so polynomial usually is written as the sum over some index set. Okay, let's call it. We don't need to call it, okay, but this is basically what we're doing. Okay, so we're summing from 0 all the way to k. The successive powers. Okay, so we have power 0. Power 1 all the way to k. So how many parameters do we have?
K plus 1.
K plus 1. Okay, so that's basically the catch. Yeah? So that's why I put the k underneath here instead of picking it up. Okay, because this is, in fact, it's very similar. It looks very, very similar. It's not equal. It's like, it's kind of like almost equal. Okay, so there's a name in mathematics for that. It's called isomorphic. Okay, so it's isomorphic. Isomorphic is like Greek for has the same shape as. Yeah, it means like it has the same shape as R k plus 1. Okay, This we haven't yet kind of fully understood what this means, okay, but this is the preview, this is what we're aiming at, okay? So other examples of vector spaces. So this is essentially, it's telling us that the space of polynomials is finite dimensional, okay? I'm going to explain what finite dimensional means very precisely in this lecture, okay? But this is the motivation for it, okay? There's other spaces of vector spaces, for example, that we've seen the following vector space, R to the power n, okay? So remember, when we write formally definition, so this is the formal definition of let's write this y to the power x. Okay, formally, okay, this is by definition. This is the set of all maps of functions, same thing. Okay, so all the functions f that go from x to y. Okay, this is a very handy notation for these spaces, okay, for many reasons. One of them is that it generalizes very quickly this one here. From a number, I can go all the way to a set. And if you remember what we did last term, a number is nothing but a set. Right? Remember what was the definition of the number d, of a natural number d? Remember that? What was this by definition? Remember how we define numbers? We started from 0 and then we defined them recursively. Right? So what was 0? Number 0 was defined to be the empty set. That's why I told you that, in fact, empty set and 0 are the same thing. But they're not, because we would like you to distinguish them. So the empty set is 0 when we're using the empty set to count. Yeah. There's other definitions of numbers which do not involve this, but this is like the one that really is the most general and works. Okay, so in fact, in some very kind of strange sense, we can consider 0 to be the empty set. Okay, and not so strange, because if you think about how you build numbers from each other, so in general, a number, remember, is basically the previous one union the previous one. So basically is this, is the set b minus 1. Okay, so I'm using here arithmetic notation, but we'll have to use that after that. Okay, but just to remind ourselves, is basically this, which is like a horrid notation for just saying that d is equal to b minus 1 plus 1. Okay, because that's essentially what you define. So basically you define plus 1 to be this operation among sets. Okay, so plus 1, so the set plus 1, okay, is the definition S union the set that had an S in it. Okay, this was the fundamental definition. Okay, so this is just a reminder to tell you basically that 1 is essentially a set that contains 0. And what is 2 following the definition? Well, following this definition, 2 is 1. I'm just going to copy, okay, mindlessly without even thinking about what I'm doing. Okay, union 1. And then I use the definition of 1 here to remind ourselves that this is 0, union 1. And there's an axiom in the many axioms of set theory. Okay? There's an axiom that tells you that when you do this construction, you always get something new. It's essential to have as an axiom, okay? Because eventually it tells you that numbers don't kind of cycle. Yeah? Natural numbers don't cycle. So you don't get stuck once you, so you don't go back to where you started from. You always get something which is strictly bigger than what you started from. Okay? So 2 is strictly larger than 1, okay? Meaning that these two elements are different, 0 and 1, because also this one is strictly larger than that one, and therefore it's different. And therefore, when you take the union of them, you get, let's say, a proper union. So this is not the same element which can collapse into 1. It's two different elements. So in fact, the set 2 is just the numbers from 0 to 1. And in this way, you realize very quickly that a good way of defining numbers is simply this. Okay? So this is your C programmer's favorite way of doing numbers, right? When you do a for loop, you always start from 0. Why? Because there's some kind of like useful purpose to that. Okay, that's why programming is starting from 0. It's not only to make silly jokes, okay? It's because it's kind of useful. Okay, so same thing here. So let's go back here and try to interpret this. So basically, what is RD in that interpretation? If you look at it, okay, it looks like RD is going to be x0 x d minus 1. Okay, so I'm thinking of RD here as being the functions which take input the subindex and return x of that subindex. Okay, so these are just functions from this finite set 0 d minus 1 into R. Yeah, so this. Yeah, I mean, all the possible functions, and these are just like sequences, right? Or arrays, or d-tuples. Yeah, some people they call them d-tuples. Yeah, because you have pairs and triples and quadruples and quintuples and sextuples, etc. Yeah, and then you call them d minus 1 tuples. Yeah, it's a tuple. In this case, it's a d tuple. Yeah, just because I'm starting to index with 0, I have to end with d minus 1, which is ugly. Okay, it looks horrible on the board. Of course, if you're programming, it's beautiful because it allows you to add things, and you have your memory is indexed by the right place where you start, right? So that's why people like it in programming, okay? Because then if you're adding memory to your code, you just have to add from that. Okay? That's why arrays for programmers it's better for them to start with 0. But for mathematicians like me, if I start from 0, it's going to look ugly because every time I'm going to have to end with d minus 1. Okay? This d minus 1 is too long to write. Right? So I start from 1 and I end in d. It's the same thing, right? So this is basically the reason for this notation. Okay, and this is just a generalization of that. Okay, and this, in fact, is the most general way of writing functions. Okay, so this is basically its functions that go from n into r. What are those functions? Those are the sequences that we've seen last term. Okay, so in fact, this is nothing but the set of all real-valued sequences. Okay, so we can write it like this in a kind of more light notation. Okay, it's a bit longer, but it's kind of lighter because I don't have to write too many variables, right? Such that xi belongs to r. You know, I forgot to say that this is xi belongs to r for any I from 0 to d minus 1. Right? That's what I should have written there. And this is the same thing here. Okay, so Rn is a set of all sequences which are real values, meaning that this is true for any I in n. Okay? And is this a vector space? So that's the question. Is this a vector space? Well, the key to success is if what you have in the base of this kind of set power, so if the set base is a vector space, then the power of it is going to be another vector space. Vector space, not only field. Okay, so R happens to be also a field, so it's much more than a vector space. Okay, every field is a vector space on itself, trivially, right? Because in a vector space you need plus and multiply, right? And a field already comes with a plus and multiply, right? So the vector and the scalars are the same thing in that case. Yeah, that's why I call it trivial. But in this case, the R, I'm thinking of it as being a vector space. If I raise the vector space to some power, I'm going to get another vector space. Some power in the sense of sets, right? Okay, this is very abstract, okay, but it's just like a small recipe or rule of thumb to remind you of that. Why can I do that? Because the values, you see, the values of these objects are always going to be in this vector space I started from. Right? I started from a vector space, so I can add and multiply with scalars. So basically, what I get, I can again use that operation to kind of like make these objects inherited. Yeah. So they're kind of learning from what was already done on the previous more elementary object, which was X. Yeah. So this is like very satisfying for someone who likes object-oriented programming. Yeah? Because transmitting, you're inheriting things. In some sense, you're overloading also. Yeah, because the plus that I'm going to do for sequences is not the same one that you do for the values. Okay, but the values are inherited because this is just an array of things like that. Okay, so it's an infinite array. So you can add real numbers, and therefore you can add sequences. You can multiply real numbers by real numbers, and therefore you can multiply sequences by real numbers. Be careful. I'm not saying that you can multiply two sequences together. Of course, you can also do that, but that's not interesting in this case. Well, it's interesting, but in this context, because I'm looking at Rn as a vector space, I'm not interested in the product of two sequences. Same thing you can do with polynomials, for example. Polynomials can be multiplied one with another. But strange things happen in that case. For example, if you take two degree polynomials, sorry, this is not this. Let's take two first degree polynomials, okay? Ax plus b and dx plus c. Okay? And you multiply them. What you're going to get is a second order polynomial. So you go out of where you started from, right? So you can still multiply polynomials, but it's a more complex operation. It's not a vector space operation. It's not a linear operation. It's non-linear. Okay? So what we're interested in here is linear things. Okay? So basically, that's why we're doing these examples and we're just looking at the products. Okay? So the same thing happens for any set. Okay? So any set, I don't know, omega. Yeah? You can take all the functions that go from omega and are real value, and this is a vector space. Okay, and this is basically the topic, the subject of functional analysis. Okay, studies vector spaces of this type. Yeah, where omega has some feature. For example, it could be the interval 0, 1. Okay, this is a huge space with respect to Rn. Right, this is a huge space because it has not only infinitely many parameters, which are the numbers between 0 and 1, but as we've seen in the first part of the course, is that the amount of numbers, of real numbers between 0 and 1 is uncountable. Remember the Cantor-Diagonal argument? Okay? So it means that it's much more than this. Okay, because in that case the cardinality of this would be bigger than the cardinality of this one, strictly bigger. So this is really like a very, very large guy. Okay? Still it's very useful because it represents all the real value functions on the interval 0, 1, which are very useful functions. So it is studied, okay, for its own sake. Okay, but this is not the topic of what we want to do. What we want to do here, we want to keep it simple. We're going to work about finite dimensions. Okay, so basically these are going to be our objects of interest. Okay, but sometimes we're going to talk about polynomials, and we're going to see that these things are useful also for like differentiable functions and stuff like that. Okay? So these are things that can be used also to do lots of analysis. Okay? So linear algebra is not confined to itself. It's actually very useful in analysis. Okay. Subspace. So what is a subspace? A subspace is essentially, it's itself a vector space, but when we are regarding it as a subset of some larger vector space. Okay, so we start from a larger vector space, say for example Rd, okay, and then we look at all its subspaces. Of course, there are trivial subspaces, okay, which are the zero element and the space itself. Those are called the trivial subspaces. Okay, it's the smallest subspace that you can have in Rd that's 0. We're excluding the empty set. Okay, the empty set in some sense is a vector space, but that's like a very silly one. Okay, so we don't think of the empty set as being a vector space. Usually we don't worry about it. Okay, so all our vector spaces are non-empty. And the Rd itself is also a vector space, and it lives in Rd, and therefore it is a subspace. Okay, but then we have all the other ones, and there's many, many of them. For example, all the lines in the plane are subspaces, but some of them are vector subspaces, some of them are just affine subspaces. The difference between a vector subspace and an affine subspace is that the vector subspace is not only geometrically a subspace, but it's also algebraically a subspace. Meaning that if you do linear algebra operations, you stay within that space. Okay, and the main example was this picture here. Remember, we had drawn two pictures. Okay, we had one space that was going to the origin, one subspace that was going to the origin that was some line, yeah, and then we had another line which was not going to the origin. And we realized that this one here is much more well behaved from an algebraic point of view, in the sense that if I took linear combinations of elements in it, I would stay in it. So there's no going outside. Whereas here, as you can see from the picture, if you take this vector here and this vector here, and you sum them, then you pop out of that space. Okay, so it's not good. It's not invariant with respect to the linear combinations. And therefore, this one here is much more special. And we will see why, from an algebraic point of view, this is an important definition. Okay, so vector subspace is one that is closed with respect to the linear combinations. Okay, so essentially, you can define it very quickly like this, and it's a good idea to remember definitions at this time. Okay, so we say that V is a subspace of some other vector space. Okay, vector space. If and only if the following happens, you start from. So what are your ingredients to do linear combinations? What do you need to do a linear combination, a finite linear combination? What do you need? What are the ingredients to do a finite linear combination? How to cook a linear combination? Okay, you need ingredients. Okay, so all these definitions, by now you understand, it's like a recipe. Yeah. So what do we need? So let's write it down. What is a linear combination? The simplest linear combination you can think of is this one. It's a bit unnerving, right? That I'm not even writing the mu, right? So people don't like it like this. Okay, but if you think about it, this is enough to generate all the linear combinations. Okay, so suppose you want to generate this. So this is linear combination. So this is the most general way of writing a linear combination. It's finite, okay? It stops at some point, right? But all these linear combinations can be generated by, like the simplest move that you can do is this one, okay? That's also known as an AXP. Yeah? So in computing, this is known as an AXP. On xy, okay? Because it means a times x plus y, yeah? It's like this, okay? So if you go and you look at the implementation of linear algebra in many libraries, they all do AXPs and GAXPs. So a GAXP is a generalized, sometimes you see also this horrible word written somewhere, you know, a GAXP, and you're asking, what is a GAXP? And it's just a joke, you know. So it's a generalized a times x plus y. Yeah. So people make up strange terminology just because it's fun. Yeah. But in fact, it's also useful, okay, because in fact that one there you can do it by repeating XPs. Okay. So what would be your first x and your first y to do the first one? Well, you start with y equals 0, a equal lambda 1, and x equal x1. And then you use y from the previous steps, which is, so now y becomes lambda 1 x1, and you add to it lambda 2 times x2, and so on and so forth. So you make a for loop, and you end up having this linear combination. Okay, so this is the most elementary linear combination you can think of. Okay, now people in maths, they have also their own traditions and their idiosyncrasies. They add a redundant mu there, just because it's fun. But you can do all the definitions without that mu, right? So we say that V is a subset of W. So what are the ingredients? The ingredients are two coefficients. One of them is too much. Okay? This is how you do it in order for the cake to be. So think of it as being sugar. Yeah. So you're putting more sugar in your cake just because it tastes better, right? And then you take two elements of the vector space, of the subspace, okay? And these are, of course, scalars, okay, and this implies that lambda equals mu y also belongs to V. Okay, so this is like in symbols, the fact that V is algebraically closed. Well, sorry, I said algebraically closed, I shouldn't say that. I should say linearly algebraically closed, or closed with respect to linear combinations. It just looks. Okay, because algebraically closed means something different in maths. So it's got nothing to do with it. Okay. So, yeah, so that's it. This is the definition of subspace. And we have seen examples, okay, many examples of subspaces, okay. And then we talked about linear combinations. So linear combinations, we already seen that, okay. Linear combinations. So these are like the basic constructs that we need to do linear algebra, okay? And we saw that we can do two things with linear combinations. We can define two very important concepts in linear algebra. The most fundamental concepts in linear algebra are the following: is independence, independent sets, vectors. Sometimes they are also known as systems, because this terminology comes from many different traditions. Okay, some people call them sets, some people call them systems, some people call them lists. Etc. Yeah? We looked only, because we're going to do finite dimensional vector spaces only, we look at finite lists. Okay, so we look at finite sets. Okay, so let's take a set. Let's call it, I don't know, S. Okay, so S to be a set of vectors. Okay, let's call them V1 all the way to Vk. Some vectors in a vector space. Yeah. When is it that we say that this is an independent set? Some people also call it a free set. Freedom, independence means very, very similar things. Okay, so we say that this is a free set when there's no way of binding one element to the others via linear combinations. Okay, because here we're talking about linear independence and linear. Okay, so we should say here linear independent sets of vectors. Yeah. So what are the linearly independent sets of vectors? Are sets that cannot be linearly independent. Okay. So this is one good way of remembering. Okay. So it cannot be. So we say that. So it's easier to remember the dependence property than the independence at the beginning. Okay. And then with time you learn, with experience you will learn that the definition for independence becomes useful. Okay, so let's not remind ourselves what does dependent mean. Dependent means this. We say that S is dependent, is linearly dependent. If and only if the following happens. It means that one of these vectors V can be expressed as a linear combination of the others. In other words, so it means this. It means that one of them, let's say J, yeah? Vj is equal to the sum of all the other ones. Okay, so all the i's going from 1 to k, but different than j. Okay, so this is excluding the j when I encounter it here, right? Time sign coefficients, let's call them lambda. Okay, so lambda or alpha. We'll call them alpha. Alpha I times VR, right? That's the linear combination. Which is the same thing as saying that this is 0. Which is the same thing as saying that lambda I, vi, and now I don't need to exclude anymore because the lambda j is 1 and is included here. Okay, so this is I going from 1 to k equals 0. Okay, and this is the definition of linear independent. Okay, so it means that there is one set of parameters, lambda, of which one of them is non-zero. We call it j here, okay, but it could be anyone. Yeah. So one of them is non-zero, and it makes the linear combination 0. So the linear combination can be collapsed to 0 by a set of non-zero coefficients. Okay. Let's do a very simple example that reminds us. Okay? Let's take two vectors which are on the same line. This is what it means to be linear independent geometrically. It means that they are in the same subspace. Yeah. Okay. Let's take two vectors. For example, let's take 1, 1. Okay. And let's take another vector. Pick another vector on this line. Yeah, so this is the line x equal y. Yeah? So this line is x1 minus x2 equals 0. Right? It's a very easy one, right? So 1, 1 belongs to that because 1 minus 1 is equal to 0. Right? Can you give me another element there? I don't know. Minus 2, minus 2. Right? So minus 2, minus 2. Works, right? So how can you find two coefficients that will make this sum be a 0 vector? Challenge. So let's call this one to be V2 and that one V1. Find lambda 1 and lambda 2 such that lambda 1 and V1 is lambda 2 and V2 equals 0. Find the lambdas. Find the lambdas. Find if you think about it, this is really a linear system, right? So did you find the lambdas? Well, it's easy to solve by visually this, okay? How much do you have to multiply V2 to become the opposite of V1? By half, right? Because if you multiply by half, you're going to get scaled to here, right? That's going to be exactly the opposite of V1. And then you turn the half into a minus a half, and then you go. So basically, take 1 and minus a half, right? So 1 V1 minus a half V2. So 1 V1 minus a half V2 is equal to 0. Right? So that's the solution to my problem. Okay? So that's how you could solve this this problem. Okay? But suppose you were being a bit not so geometric, okay? And you say, I want to solve that. Then how would you do it? You would go for V1. So what is V1? V1 is 1, 1, right? So you have lambda 1, 1, 1 plus lambda 2 and minus 2, minus 2. And you want this to be equal to the vector 0, 0. So basically what you're doing is you're setting up a linear system. Okay, so this is the connection between solving linear equations and subspaces. You see? And of course, if you solve this linear system, it's the same thing as using the matrix 1 minus 2, 1 minus 2 applied. That's what we're doing. Okay? So we're solving a linear system which has 0 on the right hand side. That's called a homogeneous linear system. Okay? So this is when this is 0, we call it homogeneous. Homogeneous or homogeneous. Yeah, it's the same thing. Right? Some people say homogeneous, some people say homogeneous. Right? That's known as a homogeneous system. Okay. So you see, this is the connection between linear dependent. Okay, so that's linearly dependent. So linear dependent means that essentially the system formed by the matrix V times the vector lambda is equal to 0, where the matrix V is simply the matrix that has columns, where V is the matrix that has those V's as columns. Okay, so from a programmer's point of view, it's the same thing as a set S, right? Because that's what you would do if you were programming. You put them in an array, right? So you would create this list, and then you call it sometimes a list, sometimes an array, sometimes a matrix, whatever. And sometimes a set. Yeah, you have to start somewhere. Okay. So in mathematics, sets are like unordered things, but in practice, you always have to start somewhere, right? So it's just their purpose is different. Okay, so an independent set is equivalent to having a matrix which has a non-zero solution to a 0 right-hand side. And this is exactly a singular matrix. Because if the matrix is invertible, it means that the only solution to the 0 system must be 0. It's necessary, right? Think about it. If you think about this being invertible, you're thinking of it as being a map, right? It's a map that goes from a certain space into another one. In fact, it goes from the space of parameters, which in that example is happens to be 2, right? Into the space of outputs, which happens also to be 2 there, right? But we could have been doing that in 3D, and then would have an extra number, right? Because we would have that. Yeah, so it would not necessarily be a square matrix. It could be a rectangular, right? So we have this rectangular system, okay, that has more than one solution to one value. So basically, for one value, 0, you would have more than one, because 0 is always a solution of the system, right? V of 0 is equal to 0, right? No matter what matrix V you take, if you multiply it with 0, you're going to get 0. Okay, that's an algebraic fact. Yeah? So if you have another one that also gives you 0, it means that your map, the map generated by this V, is not injective, right? Because it has 2 guys shooting on the same guy. Remember the shooting arrows? It's not injective, and therefore it's not invertible. So you cannot go back because you don't know which way to go because you have 2 of them. Right? Okay, so this is essentially linear algebra. Okay, so I've told you the whole story. Okay, this is essentially what we're after. Okay, so let's see how we can proceed from here. Okay, so once we have independent sets, okay, so of course I didn't tell you what independent means. Okay, so independent means the opposite of that, right? So when we say that a set of vectors is independent, so I'm going to rewrite it here on the board. Okay, so when this is wrong, okay, when this is not true, okay, so let's erase the picture. And let's look at the definition. So the definition here is basically this. So this was just a pre-definition because it was just helping us to understand what is the definition of. So if and only if there is, so I'm still independent. Okay, so if there is a lambda which is different than 0 in Rk, okay, because there's k vectors, k parameters. Okay, what are k parameters? I've got writing as Rk. Okay, so you see, this is the first of R something that's coming because I started from a vector space that could be quite abstract. Could be polynomials, could be functions, could be sequences, anything. Okay, so I can use this concept for all these objects, yeah, which are elements of vector space. Okay, such that the array V. So in general, V is not necessarily a fact because it could be just, so it's just a row. Okay, so in our notational convention, we write a capital letter for a row of lowercase versions of that letter. Yeah? So if we have the vectors v, we just write capital V. Okay? If these happen to be elements of Rk, of Rd, sorry, not Rk, but Rd, yeah, some other d, which could be k or not, yeah, then I would write boldface, right? And then I would boldface this guy. Okay, so on and so forth. So every time I do the same thing. Yeah? This way we have a kind of neat convention for our notation. And this means that this vector multiplies lambda. Now the lambda belongs to Rk, so I have to underline it, okay, because that's a fact vector. Okay? And this is basically what this means. Okay? And this 0 here is a 0 of v. Okay, so that's why I didn't underline it in the start, okay, because it doesn't have to be. Okay, so this is also something we do not very often. Okay, so we usually don't say the 0 of what. Okay, that's the 0 of v. Okay, so the linearly independent is when this is false, when this statement is false. So how do you negate there is a lambda different than 0 such that this is equal to 0? Well, you said for any lambda, this equals 0 implies that lambda must be 0. Okay? So that's the definition of linearly independent. So the only way you can nullify v lambda is by taking lambda itself to be null, which is saying that v is not singular. Okay? Now, not being singular is not enough for invertibility, because you might be shooting in a too large place. Yeah? So this happens essentially when the two spaces have the same dimension. Okay, that's also a very important result in linear algebra. Okay, so we're going to go to that. Okay, so then let's write down the definition now. So it's linearly independent. So allow me to do that. Okay, to change the whole thing. Say it's linearly independent if for any lambda equal to 0 or not, or for any lambda in Rk, if v lambda is equal to 0, I'm going to write it in one shot here. Okay, so like this. So now you understand that this means linear combination of parameters lambda with vectors v. Okay, this implies that lambda is equal to 0. Okay, that's linear independence. So understanding the space, and it turns out to be a space, okay, of all vectors that are 0 for a certain matrix V, or a linear, a set of linear vectors, sorry, a set of vectors in a vector space, okay, is crucial, okay, and there's a name for this space. This is called the null space. Okay, that's another definition that I'm going to introduce. Okay, so this is one thing you can do with linear combinations. And then there's a counterpart to that one. So this is how many branches of mathematics are developed. Okay? You do one thing and then another thing. And the two things are kind of like, they go hand in hand. Okay? So you do plus and you do minus. You do intersection, you do union. You do max, you do min. Okay, so these are kind of like dual constructions. Okay, here we do independent sets, and here we do spans. Okay, so spans. What are the spans? So the span is basically, so given a set. And again, I'm going to do this only for finite sets. Okay, so let me stick to finite sets. Vectors V. Okay, the span in S is by definition the set of all possible linear combinations lambda I V R from 1 all the way to K, okay,
with lambda in R closed.
So basically, this is the set of all the possible linear combinations. That's why we call them combinations, okay? Because we try to combine them in all the possible ways and see what we get. What we get turns out to be a vector subspace. Okay, so it turns out it's a subspace. So we have built two subspaces here. Okay? One is the null space of a given set of vectors. Another one is all the possible combinations of that. Okay? And both of them can be very neatly reconnected to the geometric introduction that we did at the beginning of the course. Right? Because at the beginning of the course we did two things. We looked at lines, for example, and then we looked at planes. Okay? And we had two descriptions for lines and planes. Okay? One of them was parametric. Parametric means that you take parallel vectors to your space, okay? And then you take all the possible linear combinations, okay? So you look at the span of that space, and then you move it to one point that goes to the space, and you realize that you've described the whole space, okay? That's this view, okay? So this conforms with the parametric view of geometric objects. And this one here corresponds with the implicit view. Remember the implicit view? The implicit view was to find equations such that the solution of those linear equations, in that case there was a b here, right? That's because our set was not necessarily going through the origin. Okay, but if we're looking at sets going through the origin, we put a 0 here, okay? And we're looking at all the vectors v that have this solution. And we saw that there's a correspondence between the two, right? So one was kind of dual to the other, right? So there's always a way to go from one to the other. That's why these two notions are dual one from the other. Okay, so that's why they're important. Okay, so this is the span. By the way, the span also can be characterized in a more abstract way. Okay, which sometimes is useful to have. Okay, if this is equal. Okay, I'm not going to prove it, but I'm just going to. In fact, the proof is not very hard. Okay, but you can think of the span of S to be the intersection of a certain family of subspaces of V. In fact, we can take all the subspaces of V. Okay, and the nice thing about this definition is that it goes beyond finite dimensional. Okay, that's why it's also important to see it geometrically. Okay, so we're taking the intersection of the following family. We take all the spaces, the subspaces of V. So we'll take all the subspaces V subspace. So when I say subspace, I mean linear subspace. There's the ones that contain the 0, right? So V subspace of V. Okay, so whenever I say subspace without mentioning, I mean a vector subspace, yeah? So it's a subset which is a vector space itself, right? Of V, such that S is a subset, because S is not a space, right? S is just a set. Okay? You see, it's a finite set. Some vectors, right? Here. Okay? It's finite. The only finite vector space is 0. R already is infinite, yeah? Okay? So vector spaces are much larger than sets. They're very, right? Whereas here I'm just take some points, yeah? Okay? So this set of points must be a subset of this. See what I'm doing here? I'm taking all the subspace. Of course, this family here, this collection of subspaces, is not empty, right? Because V itself satisfies this property, trivially, right? It's not empty. So I can take its intersection. Intersection means those who satisfy all of it. Okay, so it turns out that this is a subspace and it's equal actually to the span. Okay, this allows you to do it without having to use the linear combinations. Okay, for you as a computer scientist, this is very important. It's strange, but it's very important because there's quite a recent theory which is known as the theory of matroids. Okay, so matroids are very complicated
mathematical objects. Okay? They're abstractions of vector spaces, but also other objects that appear very much in computer science. For example, graphs. So sometimes maybe you heard the word spanning tree, or maximal spanning tree, or minimal spanning tree, or stuff like that. Okay? So that spanning in the spanning tree is the same construct as span, in a very kind of in a very different way, but you can use this kind of construction. Okay? So this construction here is a bit more abstract. It allows you to apply linear algebra to work on graphs. Okay? And there's actually a very nice connection between graph theory and linear algebra, which allows you to do lots of things. Okay? So that's another, let's say, use of linear algebra is to do graph theory. Okay, good. So I think at this point, we're going to stop here for today, and we're going to continue next time with all the applications of these to matrix algebra and solution of linear systems.